This device, which you may recognize, is an electrical transformer. If we put a direct current through one of these coils, nothing happens. However, if we change the current to an alternating current, which reverses direction many times a second, you'll see a current appear in the second coil. This very simple distinction is the reason why every national grid on Earth runs on an alternating current, like this. But at the beginning of the electrical age, we did not know this yet. One man in particular, Thomas Edison, the founder of General Electric, was convinced that a steady, direct current was the future. Meanwhile, Nikola Tesla, a former employee of his, believed otherwise. The ensuing feud between these two geniuses is now remembered as the War of the Electric Currents, and in this video, we are going to go through the full story. Best of all, we'll see that the winner was not decided by marketing, politics, or who was the better inventor. It's just basic physics. By the end, you will know why AC electricity is used worldwide, and why it couldn't be any other way. The year is 1882. Thomas Edison flicks a switch and lights up a small area of Manhattan, New York. The crowd cheers. The newspapers call it the dawn of the electrical age. There's just one problem. The furthest he can send power is about a mile from his DC generator. Any further, and the copper wires between the lights and the generator would start to melt. The reason for this is this very simple equation, which states that the power dissipated by a wire when a current passes through it is the current squared times the resistance. This power loss, which we'll plot as a function of R, was so huge that the wires would glow red hot. But this might seem quite strange, as these wires are made of copper, which is a very good conductor. Even 2 miles worth of copper cable only has a resistance of about 0.2 ohms. So the resistance clearly isn't the problem here, it's the current. But why was this current so huge? Well, to light up a neighborhood of Edison's size, which we'll say is about 500 lamps, you need about 40,000 watts of power. However, these lamps operate at around 110 volts. If the voltage is much higher than this, they'll just explode. As the power is equal to the current times the voltage, the current needed is about 364 amps. This is absolutely huge. Even through 0.1 ohms of resistance, the power dissipated at this current is 13,000 watts. That's already a third of the power generated, and this is only for a few street lamps. If the power needed increases, the current scales rapidly, and the losses just get ridiculous. And this is only at 1 mile. The only way to make this power loss reasonable is to shorten the wires, but that obviously defeats the point of this whole thing. But what if we could change the voltage? If we could step it up to say 100,000 volts, then to get the same power we need, we'd only need 0.4 amps of current. Now the power loss drops to only a fraction of a watt for the same power in, and just like that, the problem vanishes. So the solution is obvious. We need to step the voltage up for the journey and then step it back down before it enters the lights, unless we want them to explode. And this is exactly where Edison and his DC electricity hit the wall. With DC, there is no easy way to step the voltage up or down. You are stuck with whatever you generated. This meant that Edison would have had to have built a power station every mile. If we stuck with his technology, to power New York City right now, we'd need hundreds of power stations in the city alone. But today, New York City runs on just a few dozen stations. How is this possible? The answer lies in a device so simple it almost feels like cheating. Back in 1831, Michael Faraday wrapped 2 separate coils of wire around a ring of soft iron. He connected one coil to a battery and the other to a galvanometer, which measures current spikes. When he closed the switch, something strange happened. The meter spiked and then immediately went dead. The current in the first coil was flowing, but the second coil had stopped responding. Then, when he opened the switch, the meter spiked again, but in the opposite direction. Why was this happening? The answer lies inside the iron core. When electric current flows, it creates a magnetic field in the regions around it. Iron is particularly receptive to magnetic fields, and when current flows, a field appears the whole way around this core, including right through the second coil. Here I've denoted the field with a set of purple vectors. When the current is flowing, the field is static, but when the current is changing, the field changes. Faraday realized that the current spikes in the second coil were occurring only when the magnetic field was changing. If we continually flick our switch on and off, we can observe a continuously alternating current in the second coil. All this is happening because the magnetic field is continuously growing and collapsing. To describe this effect, we use Faraday's law, which states that the electromotive force, or EMF for short, generated by a magnetic field is equal to minus the change in magnetic flux. In a transformer, we write this as minus the number of turns in the coil times the flux through the magnetic core. We won't go into the details of why this law is true in this video, but if you're looking for some in-depth derivations, the Faraday's Law Wikipedia page is pretty good. Also, if you're wondering about why magnetic fields are linked to currents in the first place, this video by Veritasium is a nice visual starting point. To be clear though, Faraday's law was first proposed and verified after creating this exact experimental setup. Other derivations came later. Anyway, this is why Edison's DC failed. If we plot the graphs of the voltage in each coil, we can see that DC is constant, and as a result, there is no voltage on the other side, until we open or close the switch. But let's imagine that we can replace our battery with an alternating voltage source, which generates a sinusoidal, alternating current in the first coil. Now, the current, and therefore the magnetic field, are constantly changing. As a result, we now get consistent, alternating current in the second coil, which is perfectly timed with the current in the first coil. But this isn't even the best part. You may notice that we have a different number of coil turns in the second coil compared to the first. The EMF generated by the magnetic field is scaled depending on how many coil turns there are. The reason for this is because in each turn there are electrons, and each turn in the coil receives a voltage kick from the magnetic field. The more turns there are, the more voltage kicks the wire gets. This is why the total EMF is the number of coil turns N times the change in the magnetic flux. If we are to replace our second coil with a coil with more turns, we see that the maximum voltage is now larger. The voltage also depends on the first coil. Using Faraday's law inversely, we see the EMF in the first coil results in a change in the magnetic flux that increases as the number of turns decreases. If we rearrange our two equations and combine them, given the change in flux is the same on both sides, we see that EMF1 over N1 is equal to EMF2 over N2. Rearranged, we find that the EMF in the second coil is N2 over M1 times the input EMF. So, if we change the first coil to have fewer turns, put the same AC voltage source in, we get an even larger voltage in the second coil. This is the trick that saved the world. Using transformers, we can change the voltage from a low input to a huge output, and vice versa. This can be done easily and safely, as long as we use an alternating current. So the transformer was the weapon that won the war of the currents. Returning to our situation from earlier, using an AC generator, we'll step the voltage up to a huge value for transmission, then step it down at our destination. In 1896, Tesla and his business partner George Westinghouse achieved this exact scenario. Using the energy of the Niagara Falls, they generated AC electricity, stepped it up with transformers, sent it 22 miles to the city of Buffalo, then stepped it down, all with minimal losses. This great success infuriated Edison, who launched a smear campaign to brand AC as dangerous. He went as far as to electrocute animals, including elephants, and actually funded the invention of the lethal electric chair. But in the end, none of this mattered, as physics doesn't care about marketing. AC electricity is simply superior for long distances, and to this day, every national grid in the world runs on the principles of Faraday and Tesla. Over the next few videos, we'll be covering the fundamentals of AC electricity. In this video, we stated why we use alternating currents in the first place, but there are many details we've skipped over. Firstly, we haven't actually figured out how to generate AC electricity to begin with. What actually is this alternating voltage source that we've used? In the next video, we'll talk about AC generators and find out that, interestingly enough, they work using the exact same law we've just learned. By the way, if you enjoyed this video and like testing your physics knowledge, you're welcome to check out the Decipher Physics app, which is completely free and has over 100 questions for you to work through. Thanks for watching.